Hello, everybody. Welcome to the Audio Precision webinar. Today we'll be discussing MEMS microphone test with the new APx517B. Daniel Knighten will be leading the conversation and providing demonstrations in APX 500 software. My name is Paige, and as the producer of the event, I would like to go over a couple housekeeping items before we get started. So first, please note that this session is being recorded, and the recording will be shared with you early next week, so keep a lookout for that in your email. And secondly, we welcome questions during the webinar, so you'll see a chat function on your screen. Feel free to submit those, and we will take them periodically. Now, Dan has a lot of information to share with you today, so without further ado, Dan, the floor is yours.
All right, thank you, Paige. Good morning, everybody, or good afternoon, or good evening, depending on what time zone you're joining us from. We have a relatively full agenda for this hour. My goal at the end of this hour is that you will have a good idea, really, of how to test, I'll say, kind of any microphone using APX 500 software with, I'll say, any of our analyzers. I'll try to cover basically the things you would do to test any microphone. But today we'll talk specifically and demonstrate specifically testing a digital MEMS microphone array that has a PDM or pulse density modulation output, and doing that using our APX517 analyzer and PDM-16 input module, which is a pretty specific and apt solution to this challenge. So these are the things I'll go through. Essentially the physical configuration, the analyzer and inputs themselves, test chamber, source speaker, reference microphone. Then I'll really just dive right into the software, and we'll be looking at the software as we go through how to configure the software and make some measurements using the software. And at any time as I go through this process, feel free to ask questions. I'll try to address them as I go, but I'll also try and reserve some time at the end of the presentation to address any final questions. Okay, to start with, well, why use an APX517 audio analyzer? Or I should be more clear, acoustic audio analyzer. Well, number one, this is a new product, and we'd like to show people what it can do. But really, this product is almost built for this application. It has all the specific input and output options amongst all our analyzers that make it sort of the ideal solution. And what we're going to take advantage of today specifically is, number one, there's a built-in 35-watt power amplifier. And maybe you'd normally think of that power amplifier as being used to drive a speaker that you're measuring. But today what we're going to do is use that power amplifier to drive a speaker we're going to use as the sound source when we want to measure a microphone. And since we are measuring a microphone, we'll be taking a look at the signal coming back actually from multiple microphones. One of them will be an analog reference measurement microphone. And for that, we'll be using specifically the BNC input, one of the BNC analog inputs that can provide CCP, constant current power, for that microphone. On the input side, I realize that this picture shows a Bluetooth module, but what I have physically configured today is a PDM-16 input module, which will let us interface directly to the MEMS microphones. Vivian does ask if we'll be getting access to the slides afterwards. We can make that available. I'll ask Paige to do that.
Yeah, I can send those out next week with the recording.
Great, thank you. And then as far as we actually have two different PDM modules available for APX audio analyzers. The first is just called the PDM module, And then we have a newer PDM-16 input modules. And this is just a little table of the differences between the two. The most fundamental differences, the PDM-16 module is an input-only module. It's really very specifically designed around the challenge of measuring, say, microphone arrays of the type you might use in a smart speaker, but specifically it can analyze 16 channels simultaneously, whereas our PDM module only accepts 2. And just for the benefit of everyone, PDM stands for pulse density modulation. I won't be able to elaborate on what exactly that all is in this presentation, but I'll say this. Basically, for MEMS or microelectronic mechanical systems, microphones, there are 3 kinds of outputs they have. They're MEMS microphones, which have a continuous analog voltage output. So essentially, they're just a good old-fashioned analog microphone. There are MEMS microphones that have an I²S digital output. And most commonly, the signaling scheme is pulse density modulation. And so we are addressing those types of microphones today. So apart from the 16 input channels, the other noteworthy thing is that the PDM-16 module uses a scheme that allows for a very long cable between the front panel of the analyzer and the location where you're actually measuring a microphone. And that's especially helpful if you're testing things inside of an anechoic chamber. And that pod can be up to 10 meters from the front panel of the chassis. And that uses a signaling scheme that is designed to not observe any degradation to distance. For our regular PDM module, there is a line driver accessory, but that doesn't, it makes up for or masks the issues of cable loading, but you do tend to get into some issues with reflections and ringing due to impedance mismatches. So a couple different schemes, but probably the largest issue is just the raw number of input channels you want to measure. Okay, the next part I'd like to talk about is how what's the space where we're going to physically test this system. I'll say the gold standard, and I think what we all wish we had, is a nice, large anechoic chamber, a room without any acoustic reflections, what we would call a free field. That's definitely the ideal. For cost and space constraints, I think most of us do not have access to that. The next, I'll say, maybe best choice would be a anechoic test box, which is really another kind of anechoic chamber. It's just smaller, and therefore the lowest frequency to which it has no reflections is higher. You know, I think what's probably understood by most of you is that the bigger the anechoic chamber, physically bigger, the lower the lowest frequency at which it doesn't have any internal reflections. So a test box can be a good solution because we can have a relatively small test box if, say, we're only interested in frequencies above 400 hertz. There's a direct relationship there. Now, for the demonstration today, I will actually be taking advantage of, well, what I like to call a half space test solution. So that's a fancy way of saying I've put this little circuit board, which is a MEMS microphone array evaluation board on a tabletop. And what's nice about that is that the tabletop is roughly geometrically flat, And in this case, what it means is the reflections from the tabletop itself occur at exactly the same time as the primary signal. And so I sort of don't see them. I don't get a diffraction effect, if you will. And I'm going to use an analog measurement mic that's aligned fairly close with the number 1 microphone in the array. The next question is going to be, what do we use as a speaker to generate the actual acoustic signal that we want to use to test this microphones? This is sort of an array of choices, no pun intended. I'll say that the first choice, especially if we're looking at microphones that we want to evaluate for use in voice applications, is a mouse simulator. Here we're depicting our own GRASS 44AA or AB mouse simulator. And if we want to do hands-free tests or other tests where there's a governing standard that calls for the use of a mouse simulator, then that's a pretty self-evident choice. As far as just using a regular speaker, which is a completely valid choice, the main issue that controls is the frequency range of interest and the sound pressure level that you're looking to achieve. By the frequency range of interest, I mean if you want to measure the frequency response of a microphone from 20 hertz to 20 kilohertz, well, it can be equalized, but you can't equalize from 0. You need to have a speaker that can put out some energy over the entire frequency range of interest. And so if you want to go down all the way to 20 hertz, you're going to need a pretty beefy speaker. I'm showing a professional studio monitor here, and even actually this pictured speaker doesn't go all the way to 20 hertz. Now, for many microphone applications in consumer devices, prototypically smart speakers, mobile phones, things of that nature, we're looking at measuring the microphone over the voice band, which is a much smaller frequency range. Probably most people would probably not imagine less than 100 hertz. Some people start even at 400 hertz, and typically not higher than 8 or 10 kilohertz. And in that frequency range of interest, a little 3-inch single driver speaker of the type pictured here can actually work quite effectively, and that's what I'm actually using for today's demonstration. So we'll see what that looks like. And then finally, let's talk a little bit about reference measurement microphones. So in today's setup, I'm going to use a measurement microphone to measure the microphones under test. And I'm going to do this by what I might call the simultaneous substitution technique, in that I physically placed the measurement microphone quite close to the microphones under test, so they're sort of sharing a sound field, and that does influence the selection of measurement microphone that I would use. It is not at all difficult to find a measurement microphone that has a flat magnitude response above 20 kilohertz. Both half-inch and quarter-inch microphones will do that, but I prefer, for this specific application, a quarter-inch pressure field microphone, exactly such as our own 46BD. There are a couple advantages here. Number one, the phase response, and the phase response of a measurement microphone is something that's often overlooked because we're typically looking at the magnitude response. But the phase response of a measurement microphone, even a quarter-inch microphone, is not perfectly flat to 20 kilohertz. And in particular, the phase response of a half-inch microphone begins drooping, significantly in just 2 or 3 kilohertz, as you can see in the attached chart. So one advantage of the 1/4-inch microphone is if I want to measure phase relative to my reference microphone, the reference that I'm using will be better if it's a smaller microphone. The other thing is, of course, the 1/4-inch microphone is just physically smaller, and that means that I can physically put it closer to the microphones under test without interfering with that sound field. Okay, so let's take a look at this point right at how we're going to do this. So this is a depiction of what I have set up, and exactly it sort of all comes together here. Since I have all the inputs and outputs that I need in the 517, I don't need an external power amplifier. I don't need an external microphone power supply. Everything is just directly plugging into the 517 front panel. And in this case, I have a source speaker. I have the remote PDM input pod connected to my microphone eval board. And I've got my 1/4-inch pressure field microphone connected directly into my APX front panel. I will say that this picture's depiction is a little incorrect. I actually have the 1/4-inch pressure field microphone at 90 degrees to the sound source. A little advantageous detail. At a 1/4-inch size, a free field and a pressure field microphone have a flat frequency response to 10 kilohertz. When a 1/4-inch pressure field microphone is 90 degrees incident to the sound field, it will actually have a flat response to 20 kilohertz even in a free field. So that's sort of another advantage. Is I'll say the smaller the microphone, the more flexibility you have with how it can be positioned and used in different sound fields. Okay, so just jumping over to the software. This is what it looks like when we start up APX500 software, just with default settings on a 517. And let's just go through how we're going to configure for this set of measurements. On the output side, I am going to use the power amplifier. There are 2 outputs on a 517's power amplifier, but it is a single channel or mono power amplifier. It's just conveniently, I could potentially have 2 different test stations connected and switch between them. In this case, I'm just have that speaker connected to output A. I'm going to use it in acoustic mode. That is to say, I want to be able to set my output signal level in dBSPL. In just a second, we'll calibrate that. For input 1, I'm going to use the microphone input. I have just 1 channel. I'm going to have that. I'd like to see that in acoustic units, so I'll select that. The input is unbalanced, or the BNC input. And I do need to provide CCP or constant current to this microphone. It is a 4 milliamp source. I could also potentially select 10 milliamps if I had a CCP device that required that. I'll turn on the power to the microphone. And now I'll go ahead. I'm actually, like so many of us, working from home right now, and I'm remote controlling a system in our office. And so unfortunately, I'm not physically there to put a calibrator, an acoustic calibrator on the microphone. So instead, I'm going to take advantage of the fact that we can directly read the calibration data from the microphone via the TEDS, or Transducer Electronic Data Sheet System. So that reads that out directly. The last time this was calibrated, it had a sensitivity of 1.36 millivolts per Pascal. I'll go ahead and set that sensitivity. And now immediately I'm just reading the ambient noise in our test environment. I'm going to go ahead and open up the verify connections, and I'm just going to turn on the signal generator and verify that there is a signal. And I am looking at a signal at 1 kilohertz being captured by my reference microphone from the speaker. So that's all working. And next, what I want to do is actually calibrate the speaker. I've gotten kind of lucky here. The sensitivity of this speaker is so close to our default sensitivity that it almost looks like I already calibrated it, having set the signal generator to 80 dBSPL, and I'm measuring, 81.5 dBSPL. But I'll go ahead to References, my acoustic output references, and I'm going to set my acoustic output level. I'm going to target 94 dBSPL, or almost exactly 1 Pascal, just as a handy reference point. And I'm going to ask the system to find the generator value that gives us that sound pressure level at the measured test point automatically. And there we go. Within a tenth of a dB, we're getting 94 dBSPL, and you can see, if you're curious, we get 1.16 pascals per volt at the output of the power amplifier, all the way to the acoustic signal being measured by our reference microphone. Now I'm going to go ahead and also, just for myself, I'm going to lower the bandwidth. We don't need to measure above 20 kilohertz in this situation. So just so we're not processing data we don't need to process, I'll lower that bandwidth. And now what I've done is calibrated the acoustic output level of my source speaker and my reference measurement microphone. The thing I'd like to do next is actually calibrate or equalize the frequency response of our source speaker. So what I'll do there is I'm going to add a measurement, and I'll just use the aptly called frequency response. And let's just start out by seeing what the full bandwidth frequency response of this speaker is. That's a good starting point. We won't be able to use it full band, but it's good to know what we're working with. So let's just do a 2.5 second sweep. So you can see at 1 kilohertz, we're at 94 dBSPL, and overall, this is not a bad speaker at all. It actually has a reasonably, certainly for a speaker, a reasonably flat frequency response, all the way up to about 8K. But you can see it's a small single driver speaker, and the response falls precipitously below 200 hertz. So what I can now do is I'll go to my relative level result, and I'm going to export this data. So I'll go to Show Graph Data, Export, and I just want the relative level result. And I do want all points. Okay, and now what I can do is go to my EQ function. I'll say I want to apply a relative EQ, and I'll just import my measured frequency response and invert it. Now, let's talk about the speaker a little bit. You can clearly see that it's down 20 dB at 100 hertz or so. It's down, another 20 dB down to minus 40 dB at 80 hertz, it essentially has no output level, no signal output below 80 hertz. If I try and equalize a speaker, which has 40 dB of drop, either the software will not let you do it, it will error out, or in all likelihood you'll burn up that speaker. So if I'll just say append graph data, and I'll run this measurement again with this full band equalization. Oh, no, it says, hey, the value is out of range. We just can't do that. So let's try equalizing the speaker closer to its operating range. Let's equalize from 200 hertz to 20 kilohertz. Now, the measurement worked, and you can see in this trace that we've actually gotten a pretty darn good equalization. We've got a nearly flat frequency response from the speaker at the reference measurement position from 200 hertz to 20 kilohertz, and that's what we'll use for the rest of our measurements. So now we've got this system pretty much ready to start making some measurements, in the sense we've calibrated our signal source, the speaker. We've got our measurement microphone all set up and going. So now let's go back to signal path setup and take a look at our PDM mics. One of the features that we added in APX 6.0 is you now have two input tabs. In older versions of APX software, you could only have one input module active at a time. In version 6 software, you can now have two input modules. So on input 2, I'm going to go ahead and select PDM16 as my input. And I'm going to turn on its clock output and its VDD output. And now in my input signal monitors, you can see I have two sets of results. One is the FFT of just our reference measurement microphone, and the other is the FFT on all 16 MEMS microphones. I'll go ahead, go back to verify connections, and let's just turn on the signal generator. And you can see I now get signal on both the measurement microphone and my MEMS microphones. And if I was curious, I could look at the time domain signal monitor. This one is sort of cute because here you can see the phase offsets of all 16 MEMS microphones due to their different physical positions relative to the sound source. I'll go ahead in signal path setup and add another primary result. Let's look at RMS level for our 16 PDM microphones. And this is quite useful because since I have calibrated my source speaker at the reference position, so at the reference position I have a sound pressure of 94 dB/SPL, I can actually read the sensitivity right here. I've got minus 24 dBFS, and I happen to know that the sound source is 1 Pascal. So this is minus 24 dBFS per Pascal. Now I am reading some different sensitivities on the other microphones, and those are generally trending down. There is a little bit of ambiguity here. The tolerance on these microphones is plus minus 3 dB. So there's some of that going on, but also my sound source is sufficiently close, it's only a few centimeters away, that I'm seeing the effects just of distance, the decline in sound pressure level with each doubling of distance. So there's some of that going on here. Now what I can also do is add, I'll go to my reference mic level, and I'll add a derived result to that. And you'll notice that another new result we have available is sensitivity. So let's go ahead and add comparison data is going to be PDM-16. And if I want to, I'll add a couple of the other microphones here. Bar 2. Just for fun. I could add all 16, but as you imagine, it can get a little tedious, and I don't want to make everybody wait through while I do that. And I'll go ahead and change the units here to perhaps some more familiar dBFS per Pascal. What's handy about this sensitivity measurement, which is actually really a ratio, right? What I've having the software do is calculate the ratio between the measured level at the reference microphone and the measured level of my PDM microphones, is it's really independent of the sound source. So for example, let's crank our sound source down a little bit. You'll notice now we're measuring 80 dBSPL at the reference microphone, and minus 38 dBFS at the number 1 MEMS microphone. But of course, the ratio between the two remains constant. We'll take advantage of this sort of, I'll say, natural cancellation of the source speaker when we measure frequency response. But this is quite handy because, frankly, finding there is no such thing as a measurement speaker. This is one of the interesting things about the world of audio measurement, is they're absolutely measurement microphones. And a measurement microphone is a microphone like anything, like any other microphone, but the key property is that it has a flat frequency response. There are speakers that have better and worse frequency responses, but in fact, the speaker's frequency response is a direct interaction with its environment. So there is no such thing as a speaker that has a universally flat frequency response. And so frankly, what this does is it takes the speaker out of the equation, literally, if you will. And we're just looking at the results of one microphone relative to another microphone. And this is the key to what I refer to as simultaneous substitution. Now, let's take a look at making some practical measurements. So I'm going to go ahead and I'll show 2 examples. I'm going to add acoustic response. And you'll notice that this now has results for both inputs. So let's go ahead. I'm going to, let's run this from 200 Hertz. We'll do that at 94 dBSPL. And let's apply our equalization, though I'll show you what we get when we don't do that. And let's do our 2.5 second sweep or so. Okay, so we have the impulse response of our reference microphone. We have the impulse responses of all 16 MEMS microphones. Here's the energy time curves. And then perhaps more interestingly, oh, sorry, I made a little mistake here. I forgot to invert this. So let's do that. And let's do that again. It's a good thing to check the frequency response on your reference microphone for that reason, because that's a little boo-boo on my part. But now I can see that now I've applied the EQ, I get what I expect, which is a flat frequency response at my reference microphone. And now I've got the frequency response in magnitude of all 16 PDM microphones. Perhaps more interestingly, here's the delay of all 16 microphones. And you can actually see two things here that are a little bit interesting. The first is what we expect, which is that the delay increases as the microphones at the back of the array relative to the signal source are further away. The other thing is actually there's a little defect on this board. The data lines were inverted. So the data line for microphone number 1 is actually reversed with its paired microphone in MEMS. In the typical PDM signaling scheme, every one data line is shared between 2 microphones. So you can see this little ripple through of the inversion. So it's actually, so the physical microphone number 1, its data is actually coming through on channel 2. That's what happened there. We can look at the phase response, and let's start off by looking at the phase response of our reference microphone. And here's, a classic linear phase response where we're looking really just at the delay or the time of flight from the speaker to that microphone. Here's the phase response of the 16. And here again, you can see where channel 2 is ahead in phase of channel 1, and that's because of that little design defect with the data lines on the board being screwed up. And we have all the other results, but those are probably the most material results for our purposes. And again, since I have measured, since I have calibrated the sound source to give us 1 Pascal at the reference position, I could, in theory, directly measure, the sensitivity right here, right? These are particularly, if we look at channel 2, right? That is channel 2 is where the reference microphone is parallel to or aligned to. So I can see, oh yeah, I'm getting right about minus 26 or 25 dBFS per Pascal. But I can actually do the same trick I showed you with the Rms level meter result. I'll take this guy, I'll add a derived result. I'll select sensitivity. Reference data will be PDM-16. Yep. And let's again just add a couple more for fun. I won't belabor adding all 16. But now I have the results of all of these microphones relative to the reference microphone. And again, I have the benefit, let me put this in dBFS per Pascal. If I change this test level, the ratio is the same. And let me go even a step further. I'll go ahead and disable equalization. And again, the frequency responses, there's still little odd little things here that happen because of the behavior of the speaker, but the frequency responses, again, basically come out the same. And that's, again, because by calculating this as a ratio between our reference microphone and our PDM microphones, we are removing or dividing out the source speaker. Let me just quickly address a couple questions. Todd K. Asks, if you change the PDM configuration, you can switch left and right channels based on the rising falling edge to resolve the microphone pairing. That is correct for our PDM module. I just double check here. Yeah, we did not implement the ability to swizzle the channels and software on the PDM-16 module, though that's something we may reconsider. I found the, yeah, so the question is, what is the industry standard? We go with a low is left on, you know, whether the data on the rising edge of the clock pulse should be left or right. And then Ed asks if there's a trick to add all the tracks to a comparison at once. Unfortunately, not at this time. At this time, you do have to is which to which mic. And then the last question is which traces to which mic. So let me just dive back into that for a second. So if we look at our derived result here, and we look at the derived result settings, here's the definition for each of the traces. And here I'm saying that the reference data is RMS level mic. The comparison data is PDM-16. So I'm comparing channel 1, and there's only one channel at this time to use on the reference, to channel 1 on the comparison. So that's PDM mic 1. And then on the next trace, which is trace 2, I'm comparing it to channel 2, channel 3, and so on. And that's how I would set this up. So there'd be a one-to-one relationship. You could substitute the word trace for whatever you wanted, but it would be a one-to-one relationship. Okay, I'm going to show there are many ways of, there are many measurements in APX which would get you to similar results. Let me show you one more measurement which I think is probably relevant, and that is using transfer function. And transfer function is going to have some additional useful properties for us. So in transfer function, we're going to calculate the response of, well, response is probably the wrong word. We're going to calculate the transfer function between two signals. And this is an old school technique. It's been around for a while. We added it to APX software recently, but it's not a new thing. And I'll just, I guess, gloss over this a little bit. But for our purposes, for measurement purposes, the nice thing about transfer function is most measurement techniques in the world, most audio measurement techniques in the world, are based on testing devices with a sine wave. There's all kinds of good reasons for doing that. The downside of doing that, particularly when we're measuring microphones, and particularly when we're measuring microphones that are going to be used in a voice application, is that very often the device may be doing some active signal processing and will have a non-linear response to a sine wave. In fact, to put it in short, many voice processing systems try to cancel sine waves. It's not human speech. It's not a desirable signal. The advantage of transfer function is that we can make measurements, frankly, using any signal we want. That signal can, as long as it has energy in the frequency range of interest, we can use it to make our measurement. So what I'm going to do here is actually I'm going to set up our transfer function, and we're going to measure using a speech signal, just a wave file of speech. Now, the next little bit that I do have to, I'll say cop to or admit, is one thing that is confusing is the signal generators and AP software are calibrated according to the peak level of a sine wave. If you're generating a different kind of signal, in this case a speech signal out of an APX, and it has a different crest factor, you really have to add that crest factor to the signal level in order to get, I'll say, what you might expect. So I'll just quickly say here that 114 dBSPL set in the signal generator will get me what I expect for this speech signal. I think we have a blog post up on our website that actually talks about how to find the crest factor and set a generator level depending on the non-sinusoidal signal you're generating. But for this moment, we'll just squeeze this at 114. The next things, there are a little bit more settings here than in a typical measurement in APX. The reference is the signal that's going to be compared against. And in this case, I'm actually going to set the reference to be one of my input channels. And I'll start with the reference being our analog reference microphone. Match is if I want to automatically trigger by recognizing the signal itself. That's more useful if we're doing an open loop test. In this case, I don't need to match the signals. They'll arrive at both the measurement microphone and the PDM microphones relatively simultaneously. And because I want to look at the phase data, I don't want this to be time aligned. I actually want to see the phase relative to the reference. Calculation mode, that's a setting where I'll just say that unless you know what it means, just leave it alone. I'll use a 48K FFT. That will give me a frequency resolution of 1 Hertz. And this is a 10-second long signal, and it's non-repetitive. So I want to capture the entire signal. So I'm going to do enough averages with, say, 50% overlap so I can capture the entire signal. And let's do this. Oh, have a little change of the analog input range. I do need to go into advanced settings, turn off auto ranging, and well, that's fine for right now. Now we do have a lot of results in transfer function, and approximately half of them are redundant because they're showing the transfer function between the signal and the signal itself. So for example, this result is the magnitude spectrum, the frequency response function between the mic and really the mic itself, since that's what I've chosen as the reference. We're not interested in that so much, but here we have the frequency response function between the PDM-16 inputs, all 16 PDM mics, and our reference microphone. And you'll notice, number one, this is going from 20 Hertz to 20 kilohertz. It's full range. And these responses at low and high frequency look a little bit janky. So actually, one result that I almost always like to look at first in transfer function is the coherence. And the coherence is kind of exactly what it sounds like. It is the relation, it's the how close was the signal at a given frequency in the response to the reference. And one of the things to be aware of is that the speech signal I'm using, it's a human speaker. So it doesn't have energy at all frequencies. In particular, it doesn't have energy at very low frequency, and it doesn't have energy at very high frequency. So in this range, starting at maybe 150 Hertz, all the way to between 8 and 10 kilohertz, that's where I have strong coherence. That's where there was energy in the signal at the relevant frequency. And that's the range in which my measurement results are valid. And so that's definitely something to be aware of when doing transfer function. And in fact, one reason why we often use noise is if we use broadband noise, that's going to have energy at all frequencies across the spectrum. And so here you can see, well, we have energy all the way up to 20 kilohertz, and we don't have it at low frequency because that's frankly the limitations of our speaker, but we have coherence all the way up. So we have the magnitude response, and then we have the phase response. Now we do have some funny things that are happening in the phase response because we're looking at that phase response. We start unwrapping it at low frequency, and because our results are very noisy at low frequency, it's getting the starting point for the phase is a little wacky. So now let's look at this a little bit differently. Let's look at this relative to a microphone in the array itself, because this is something real where what we really care about is what's the phase inside of the array. And so now we see sort of a much something very close to actually the ideal response. And you notice here I've set the reference microphone to be the number 2 microphone in the PDM array, which thanks to our little swizzling, we actually know is the number 1 microphone. And here we get a classic view of that phase delay from each of the microphones that's a little bit further away from the sound source than the reference microphone. Okay, so let me just try and address some of our questions in the last few minutes. Okay, so first, a question of, well, let me actually go backwards first. So question about what overlap is and what it means. So let's look at the acquired waveform. And let's just go back to our speech signal. So this is the actual speech signal. And what you can see is, human speech is not at all like a sine wave. It varies quite significantly in time. It's not a steady state signal. And typically, the thing to do with a non-repeating signal is to apply an FFT window. And the thing we have to be aware of when we apply an FFT window is that attenuates the beginning and the end of the waveform. And with a non-repeating signal like human speech, well, what happens if there's a feature of interest at the beginning or end of the waveform? It might get attenuated to nothing. So what overlap means is for this particular transfer function, we're actually performing 19 FFTs over this 10-second period of time. And so you can imagine at T0, we start an FFT, and in this case, the FFT captures the first second. The next FFT doesn't start at 1 second. It actually starts at 500 milliseconds. So it contains 50% of the overlapped 50% of the previous acquisitions data is included. So that's the overlap, as these FFTs are overlapped over each other. As to the question of, hey, well, why 50%? Why not 25 or 33 or 67 or 75%? That is, frankly, a judgment question, and it has to do with, well, how discontinuous do you think your signal is? Let's say that my test signal, for whatever reason, good or bad, was just a bunch of random clicks, randomly spaced over time. I mean, let's say somebody physically in an auditorium just had a clicker. I'd really want to make sure that I covered all of them, and so I would use a lot of overlap. Let's say my signal was white noise, you know, so a random signal, but there's kind of the same energy content in each acquisition. It's quite possible I wouldn't need any overlap. And this is an area where you're certainly absolutely welcome to just experiment. So let's go noise. Let's not do any overlap. Let's whatever. Do that. I won't make us wait for the whole period of time. But here, you know, so this is with no overlap, but using white noise. So it's a bit of a experience, or also just trial and error test. And then actually returning to an earlier question, so how does this work in sequence mode? I'll just go ahead, or bench mode. I'll just go ahead over to bench mode. And I'll set up my analog reference microphone. And then I'll go ahead and set up my PDM-16. And now I can do things like add a meter. For some reason, bandpass level comes to mind that covers PDM-16, and you'll notice that the scope and FFT monitors are also doubled up. So we do support the multi-input functionality in both bench mode and sequence mode. And then another question, do you have a hookup recommendation for analog MEMS mics measurements, especially for good noise floor? That's a very good question. Generally speaking, you can plug an analog MEMS mic directly into the analog input of an APX analyzer. APX analyzers are, you know, depending on the model, from the 555, the self noise is below a microvolt to a, you know, something like a 515 or a 517, where the self noise is in the, you know, 1.2, 1.4 microvolt range. You can make a decision as to whether you need external gain, but generally my experience is that you can just directly measure analog MEMS mics. You don't have to make a provision for external gain unless it's a super low noise microphone. Okay, So I've basically used up all of our time. We're a couple minutes over, but I'd be happy to entertain any additional questions, or if there's anything you would like to see. And of course, we are also available via all our normal tech support channels and our field staff. So always please feel free to contact us with any questions you have. But if anybody has any additional questions, feel free to submit them now.
Excellent. And everybody, there is a chat window. You can go ahead and submit your questions via the chat. While we wait to see if we have any other questions today, I just wanted to let you know about, and Dan already mentioned this, the Audio Precision blog. So if you go to www.ap.com/blog, we regularly publish great content on there about all things audio test and measurement. And we'll be posting in the next couple weeks a review blog post on this webinar. So if you want to learn more, be sure to check that out as well. And of course, I'll be sending an email next week with a link to the recording of this session as well.
Okay. Well, I would like to thank everybody for your time. It's fun to put these on. I hope I'm not the only person who likes messing around with technical equipment and is curious about audio measurements. If oh, I've got one more question. Any advice on decimation settings? That is a good question. So I don't have any advice on decimation settings. Decimation settings are, so this is exactly what's being referred to is a MEMS, a PDM signal, a pulse density modulation signal, is basically the raw output of a sigma delta modulator. I won't go into the whole explanation of that, but the quick and dirty of it is that it's a 1-bit A to D converter, as bizarre as that might sound. And it comes out at a pretty high rate. So in this case, in my current configuration, it's coming out at 3 megahertz. And we then decimate or low pass filter that to actually demodulate the baseband audio. And the question is, well, at what rate should you do that? Because there's actually a lot of selections available in our software. And that is usually a design question. It's a question of both the specifications of the microphone itself, what bandwidth it's designed to operate over, and it's a question of the application you are using it. So if I decimate it at a lower rate, I will see a wider output signal. You know, so if I decimate this signal at 32x or 1/32, now in theory my signal output is coming in at higher than 48K. And if I decimate it at a higher rate, let's go crazy. I get almost no signal. Let's not go too crazy. So it's kind of, usually it's defined either in a spec sheet or in a product definition for your design. And it's not usually something that, you know, we sort of advise from the audio analyzer perspective. It's just, it's actually directly equivalent to sample rate, I would say. It's, you know, the question that's being asked is essentially a version of what sample rate should I test at? Let's see if I can give a quick overview of PDM. So one way to view PDM is this. Imagine you have a comparator, And it's very simple. If the signal that comes into the comparator is a positive voltage, you get a 1. And if the signal that comes into the comparator is a negative voltage, you get a 0. So that's sort of the 1-bit A to D converter. Now, I think we're all thinking, well, how can you possibly extract an audio signal from that? So that actual bit of mathematical magic is a bit above me, but I'll give you the textbook answer, which is that we do this comparison at a very high rate, so exactly maybe 3 megahertz, and we have a mathematical algorithm, a set of feedback and feed-forward loops that push the quantization noise produced by that up above the frequency range of interest, or the audio band, for our applications. So there's a bunch of energy up above 20 kilohertz. So the way we extract the audio from a PDM bit stream is actually pretty straightforward. The creation of a PDM bit stream, I'll go ahead and just say that that's black magic. The way you use a 1-bit converter and modulate it and push the quantization noise out of the baseband and all of that, that is beyond my ken. But the way we get audio back out of a PDM signal is actually very simple. All the noise is above 20 kilohertz. So we just have to low pass filter and sample rate convert the signal. So we'll take a 3 megahertz signal, low pass filter it, that is, remove all the energy above our frequency range of interest, 20 kilohertz, and then we sample rate convert the 3 megahertz to, say, 48 kilohertz. That's how we get back to an audio signal.
Find out more at Vicom's website.